Welcome back, and in this video we're going to be looking at the electron structure. Now you've studied electron structure before at GCSE level, but at GCSE level you only used a very basic model. At A level we need a slightly more advanced model to understand exactly what's going on with the electrons in their shells, subshells and orbitals. It takes a bit of getting used to at the start, but eventually you'll see how it relates to the periodic table and the reactivity of the elements. So here we have a section of the London Underground map. Now the London Underground map is a model. It's a model of the underground tube system in London, but it doesn't actually represent reality. So for example, if you look at Victoria Station and you draw a line to South Kensington, it looks like it's a straight line between those two stations. But as anybody will know who's been on that tube, it's not a straight journey. It goes round bends, it goes up and down, goes round corners. But this is a useful model if I want to navigate my way between Victoria and South Kensington, or between Green Park and Euston, or any other point on the London Underground map. But it does not necessarily represent reality. This is very similar to the version of electron structure that you've been looking at GCSE level. It was a good model for that level, but at A level we need to look at it in a little bit more detail. So this is a more detailed map of the South Kensington area. We've moved on from the London Underground map, which is very basic, to this map which gives us a little bit more information. So this is like moving from your GCSE model of electron structure to an A-level model. It's still not perfect, and you would need to be studying chemistry at undergraduate level to be going on to the next stage. So we're looking at the arrangement of the electrons in the atom, and we're on page 1 of your notes. So electrons can only be found in these specific energy levels. We call them quantum shells. They fill up from the shell closest to the nucleus first. The reason they do that is the shell closest to the nucleus has the lowest energy, and as the shells get further from the nucleus they gain energy. If an electron moves from a lower to a higher energy level, it has to absorb a particular quantum of energy. Likewise, if it drops from the higher energy level to the lower, that quantum of energy is released. And electron shells can only hold a maximum number of electrons. So in shell 1, the one nearest to nucleus, we can get a maximum of 2 electrons. In the next shell, shell 2, we can only have 8 electrons. In shell 3, we can take 18 electrons. Not 8, so some of you will have learned 8, but actually it's 18. But they do fill in a slightly different order, and we'll go through that later on. So let's have a look at some dot cross diagrams. So we're going to look at the sodium atom and the sodium ion. So the sodium atom has 11 electrons in its shells. So I've got my sodium. The first shell can take 2 electrons. The next shell, draw my circles, they don't have to be precise, can take my 8 electrons, and that leaves 1 electron in this last shell. The sodium ion, on the other hand, has lost that outer shell electron, so we've got 2 electrons in the first shell. We've now got 8 electrons in the second shell, and that's my sodium positive ion. So I'm going to draw brackets around it, and it's a positive ion. So I have 2 electrons in my first shell, 8 in my second, 1 in my last. And for the sodium ion, I have 2 electrons and then 8 electrons. And that's my sodium ion and my sodium atom. I could do the same thing for the fluorine atom and the fluorine ion. So I have a fluorine atom. I have 2 electrons in the first shell, and I have 7 electrons in the second shell. The fluoride ion, on the other hand, has 2 electrons in the first shell but 8 electrons in the second shell. By convention, we generally show that extra electron as a dot rather than a cross, but we don't actually have to. So the fluorine atom has 2 electrons in its first shell and 7 electrons in its second shell, and the fluoride ion has 2 and then 8. And again, because that fluorine has gained an electron, it's become an ion, it's become a fluoride ion. And what we can now do is fill out this table with the elements, symbols, and the number of electrons in each of those quantum shells. So as we increase in atomic number, we increase in the number of electrons. And as you can see there, they increase as we go down the page. When we get to a maximum of 8 electrons, we need to go out into the next shell and start filling that one up as well. This is generally speaking where you would have stopped at GCSE level, because you would have now 9 electrons in principal quantum shell 3. So moving on, we're now looking at a more A-level model of the atom. So we still have our principal quantum shells. So we're going to call those 1, 2, and 3. So these are my principal quantum shells. And that's what you're used to dealing with at GCSE level. But these principal quantum shells can be broken down into what we call subshells. Now, in the first principal quantum shell, we only get one subshell, and we give that subshell a letter, so it has the letter S. In principal quantum shell 2, we have 2 subshells, which we call S and P. And in the third principal quantum shell, we have 3 subshells, S, P, and D. So each of these principal quantum shells can be broken down into subshells. Each of these subshells can be broken down into orbitals. Now, the S subshell is broken down into one orbital, and usually we just call it a box. Again, all the S's just have one orbital. Doesn't matter if it's 3s or 2s or 1s. The P subshells are broken down into 3 orbitals. We call them px, py, and pz. And again, doesn't matter which principal quantum shell you are in, you will still get the same 3 orbitals. D is a little more complex, but D subshell is broken down into 5 orbitals. 5 orbitals. We could go on and look at the Fs, and the Fs are broken down into 7 orbitals. So that's how we actually break down the electrons, their shells, subshells, and orbitals. So, as I said, at GCSE level, you've been used to dealing with principal quantum shells, but you have to understand that there's a layer inside that, and they're broken down first into subshells and then into orbitals. So these different subshells contain different numbers of orbitals. Now, an orbital is simply a region of space where there is a probability of finding an electron. It's not a certainty. Once you get onto the quantum level, things become very weird, and we cannot actually tell with any certainty where the electron is and how fast it's moving. So we talk about probabilities of finding an electron, rather than saying that that is definitely where the electron is. An orbital can only hold a maximum of 2 electrons. They have what we call opposite spins. This is sometimes called spin pairing, and that reduces the repulsion between the 2 electrons. So we have this little table to fill in. We still have our principal quantum shells, 1, 2, 3, and 4, and they are broken down into these subshells, which are then broken down into orbitals. So the S subshell only ever has 1 orbital. We call it 1s if it's in the first principal quantum shell, 2s in the second, 3s and 4s, and so on. The P subshells, well, in the second principal quantum shell, we have the 2p, then the next shell we have 3p, and again we still have 3 called 4p. Next level up we have the d subshells, and I have 5 orbitals, and they are called after the principal quantum shell they're in, so 4d. Last but not least, we have 7 f orbitals. So the total number of electrons is 2 in principal quantum shell 1, 8, and then we've got 18 in total, and last but not least we've got 32 electrons in the fourth principal quantum shell. There is some evidence that we've actually got a G subshell, but that's for very, very heavy elements, and we're not 100% convinced about the G subshell at the moment. So I'm now just going to relate this back to something you've done many times at GCSE, a dot cross diagram. So I've got 2 electrons in my first principal quantum shell, then I've got 8 electrons, and so on. And I'm just going to do the dot cross diagram for calcium because it's a good example of what we're looking at. So I've got 2 in the first, 8 in the second, 8 again in the third, and then I've got 2 in my fourth principal quantum shell. So the circles in a dot cross diagram represent the principal quantum shells. We're going to look at how that relates to our orbitals and our subshells. So I've got 2 electrons in my first subshell. So I'm going to draw them as a little arrow up and arrow down relative to the spin pairing. But that is now full. There are no other orbitals available in the first principal quantum shell, so I move to the next energy level. And the next energy level I come to is the 2s. So I'm going to put 2 electrons in there. Now that now is full up. I can't fit any more electrons into it. I need to move to the next level up. And the next level up is the 2p. Well, I can fit more electrons into my 2p subshell because it's got more orbitals. But now that is all filled up, I need to move to my 3s because that's the next energy level up. So I'm going to put 2 electrons in there. That's now filled up, still got more electrons. They're going to go into the 3p, so I'm going to put those in. And I've still got more electrons to put in. I've got 2 more electrons to put in. Now, I've got a choice between 3d and 4s. So 3d is still in principal quantum shell 3, but you should be able to see that 4s is slightly lower in energy than the 3d. So I'm going to fill up the 4s first before I put the electrons into the 3d. So that is where my last 2 electrons go, and that's the electron configuration for calcium. It's done via energy levels. So I always go from the lowest energy level first to the highest energy level. So the first orbital to be filled would be the 1s. That's principal quantum shell 1 and subshell s. Then the next level up would be 2s, and so on. So that just finishes this little video looking at the A-level model of electron structure. It takes a little bit of getting used to, and in the next video we're going to be practicing lots of different examples and ways of using this electron structure. But hopefully it'll start to make a little bit more sense of the periodic table and also help you to understand why atoms and elements react in the way that they do. So until then, stay safe, take care, bye bye.